Welcome. So, we were continuing our discussion with on Mosfet. We had derived the current voltage equation in the last lecture. If you remember, a Mosfet Idvd, which is the output current versus output voltage relations, we had tried to derive mathematically. I told you that there are two regimes primarily, one is the linear regime, one is the saturation regime. We had derived the expression, so we will have a recap of how we had derived, and then we will move forward to discuss more important aspects like effect of substrate bias and short channel effects and so on. Okay, subthreshold slope, those are important characteristics in a MOSFET. In modern semiconductor technologies, people are moving towards low power many circuits and low power chips. So we need to scale down the power also when you are scaling down the transistor. So subthreshold slope, for example, is a very important concept. People are working on steep subthreshold transistors for extremely low power chips, that can work at very low power, but that have very high on off ratio, for high speed digital logic for a sort of application. So we'll continue from where we had left the last time, which is the IDVD relation, and from there we'll go to the effect of substrate effect and subthreshold slope and short channel effect in today and the next lecture. Okay, so let's come back to the last slide where we had left. So if you recall, this is the IDVD characteristics. This is the IDVD characteristics that we know for a transistor, a MOSFET for example. In fact, for any field effect transistor, it will look like very similar to this. The y-axis is ID, which is the drain current, and the x-axis is the VD, which is the drain voltage. So it's called output characteristics. You can see that there's a linear regime when the current increases linearly, and then there's a regime that current saturates. In this regime, the current does not depend on the voltage the drain voltage you're applying. It's actually controlled by the gate voltage. These are gate voltages. And there is a non-linear regime when it transitions from a linear to a saturation sort of a point. So we had derived the expression for the current as a function of the gate bias, as a function of the drain bias. This current was derived in the last lecture, if you recall, and this is the main expression of the current. But remembering this expression or using it to solve any problem is very difficult. So we said we'll simplify this. We'll simplify this expression. We'll have one expression for linear regime, right? We'll have one expression for linear regime here, this part, and then we'll have one expression for the saturation regime, right? When the current saturates. So the current saturates here. So if you recall, now we had done some simple approximations. I told you that if you approximate these conditions, for example, in the linear regime, let me change the color of the pen. Probably I'll take a blue one, for example. So if you take the linear regime, I can look at very close to zero bias, say here. At that point we can say that the drain voltage that you are applying is very low. It's much lower than the gate voltage times minus the threshold voltage. Then in that case we can simplify this expression, and the simplified expression, this is the theta, the body factor that comes here, don't worry about that. So in the linear regime, the current expression will look like this. Okay, so essentially the current goes linearly as the drain voltage. Of course it has to go linearly. Also it goes sort of linearly with the gate voltage minus the threshold voltage. So this quantity of Vg minus Vth is called the gate overdrive. Okay, Vg minus is gate overdrive, and then there is this Z, which is essentially W, the width of the device. Okay, the width of the device, if you recall, it's like the lateral dimension of the device. So you have W by L, so you have a Z by L, that is the width, the dimension of the device. L is the length of the device, mu is the mobility, Cox is the oxide capacitance. This is the gate overdrive, and this is the drain voltage. The current increases linearly with the drain voltage. So this is a very nice expression that you can keep in mind. I also told you that in certain textbooks, they also give another expression, another term here. So what they will write is that they will write Z by L, because it's approximation. You are essentially approximating this equation. Depending on which terms you choose to leave out or don't leave out, your approximation might give you slightly different equations, but more or less it will give you the correct answer. So this is Z by L mu n Cox. Here I have Vg minus Vth into dl. Some also textbooks write Vg minus Vth minus Vd by 2 into Vd. Okay, and this expression becomes this quantity Vd by 2, which is not here, you can include that, and this becomes more prominent in this regime when your Vd is little high. Okay, before it goes to saturation. Similarly for the saturation regime, you will also have an expression if you look at that. So the first thing to understand is that in saturation regime, your gradual channel approximation doesn't hold true, because your channel edge is now pinched off, the edge of the gate. So current will saturate, and you have understood the physical basis of saturation is that in a MOSFET, if you look back into the the diagram of a MOSFET here, at this point your gate will be pinched off with respect to the drain, because the drain is at higher voltage than the gate. So this point will be pinched off. So you will have very few electrons here, and there's a large depletion region here. Carriers will be swept away to the depletion region, to the drain, and as you apply more and more drain bias, this pinch off region will move more and more to the left side, right? And so your channel length will decrease slightly, keeps decreasing, but the current will not increase, because the voltage that you are applying, extra voltage, is dropping across this depletion region. Whatever this particular voltage will be fixed at VD set, which is the voltage at which the saturation or the pinch off occurs, right? So anyways, so to derive the saturation current, what we have to do is that we have to put the current, the charge has to be 0 at the edge of the channel, and your potential will be essentially the VD set at which it saturates. If we take a thin oxide, and if you talk about very low doping, then the voltage dropping across the oxide can be ignored, and in this case the body factor, which we have written down in the previous expression, also will be very negligible, because if an oxide is thin, then capacitance will be very high. If this is very high and doping is low, this is low, then this quantity will be very small compared to 1, and so we can neglect that. In that case, we shall be able to derive an expression for the VD set, and using that we can derive an expression for ID set, and this ID set essentially is VG minus VTH. Sorry, this is VTH. So this is whole square. Okay, so this is whole square. It depends on VG minus VT whole square, and it doesn't depend on the drain voltage. Doesn't depend on drain voltage. So doesn't depend on drain voltage. So of course you remember this part doesn't depend on the drain voltage. It depends, this locus of this point moves quadratically, and that's why it comes here as VG minus VTH square. Here this quantity also remains there. Okay. Now this is your ID in the saturation regime. Remember, there is also something called now that you are discussing this, there's something called a GM of a transistor, which you have probably come across in your analog circuits or devices class. GM is called transconductance, and transconductance defines the gain of the field effect transistor. It can give you the gain of the transistor. So you need a higher transconductance, because then you will get a higher gain in the device, and a transconductance is defined by actually the change in the drain current. Okay, the change in the output current, or the drain current is the output current, with respect to the input voltage or the gate voltage. Okay, so what means is that if you look into this plot, okay, so let me erase this part so it will become clear again. So if you look into this plot again here, you will see that with different gate biases, this is 8 volt, 6 volt, 4 volt, 2 volt, with different gate voltages you fix the drain voltage. Suppose I fix it here, then with different gate voltages from 2 to 4, 4 to 6, 6 to 8, the gate is changing by a constant amount, which is 2 volt, right? But the drain current is changing differently. I am changing here I am increasing even more, here it's increasing even more, here it's increasing even more. So the rate at which this drain current or the output current is changing, with respect to the gate voltage, okay, that is called transconductance. And essentially what is the rate at which this is increasing at a given drain voltage with respect to gate voltage, okay, that is called transconductance. And to understand transconductance, what you do is that you actually plot the this is important for any field effect transistor, by the way. You plot the drain current, which is the output current, with respect to the input voltage, which is VG, right? So for example, the Mosfet threshold voltage, suppose it is 1 volt, this is 2 volt, this is 3 volt, this is 4 volt, this is 0.5, and so on. So this is threshold voltage, for example. I'm just taking an example that the threshold voltage is 1 volt here. So in ID versus VG, this is output current, right, and this is input voltage, the gate voltage. So below, when a gate voltage is below your threshold voltage, let me change the color here. When the gate voltage is below threshold voltage, then your current will be very small, it's very negligible. At the point it is threshold voltage, the current will start increasing, and it will keep increasing, right? It will keep increasing with the gate voltage. And this is ID versus VG, okay, this is ID versus VG, and the rate of essentially this increase, how this is the slope of this, ID versus VG, this ID versus VG plot, dou ID by dou VG is actually GM, okay. And the higher GM means this slope will be higher, okay, the slope will be higher, transconductance will be higher, and the gain will be higher. So if you recall this, let me erase this again so that I can bring on the slide here, okay. So essentially this is your expression for threshold the saturation current. So what is the transconductance of a MOSFET in this regime here? So here what you can do is that you can take a derivative of this ID with respect to Vg. So what will happen is that this is your GM actually, this is your GM. So what will happen is that if you take a derivative, it will be Z mu n Cox by 2L into, this will take a derivative, so it will be 2 Vg minus Vth, that's all, right. So essentially your 2 will cancel out, and so 2 will cancel out, and so what will your GM be is that it will be Z by L mu n Cox Vg minus Vt. So that is your transconductance. So your transconductance will increase if your capacitance increases, which means epsilon by d. So d has to be smaller. If your mobility is higher, that's your transconductance will increase. That's why you need a higher mobility in a material, so that your gain also can be higher. Your L is smaller. If your L, the short channel length is short, then also your gain will be high. That's why you can go to short channel devices, so that you can get higher GM. And also of course your gate overdrive depends on that, it depends on the gate overdrive. If you apply higher gate voltage, you typically tend to get higher GM, right. So this is all about the current saturation. And what are the other points that we said we'll discuss? If you remember, we had discussed till now the current voltage relation or the gradual channel approximation to derive the expression for Idvd essentially, right. And also I showed you how Idvg looks like, the concept of GM and so on. So this is about the current voltage relation. Now the next point, and this will not take so much time here, is the effect of substrate bias on the threshold voltage. Do you know what is substrate bias? So if you recall, in a MOSFET, you will have this n plus pocket of source, n plus pocket of drain, and then there will be gate dielectric over which you have the gate here, right. And this is a p-type substrate, for example. It also has a contact here, by the way. That contact, this is called substrate, or you can call it body or substrate. So typically this is contact, the body is the substrate here is actually shorted to the source and kept at ground. This source is ground of course, and it's also connected to the ground, so it's like sorted. But in case this is not shorted to the source and grounded, but if you are applying some voltage here, Vb, I am saying B is in the bias, okay, the body, sorry, the Vb is the body. So if you apply some voltage to the body, then your threshold voltage, the voltage at which you invert the channel, will actually change. If your threshold voltage was say 0.5 volt, then applying the some it's a fourth terminal, you can say. So you are applying some voltage to the substrate, you are also going to affect the threshold voltage. So the question is, how much will that effect be? How will the threshold voltage change, which essentially some voltage that I am applying on the substrate here. Please remember that if you have a p-type substrate, which is an n channel device, if you have a p-type substrate, which means this is an n channel device, okay, if you apply a Vb which is positive, then if you apply Vb which is positive, then what will happen is that this n plus junction, this n plus and p junction will be forward biased, and if it is forward biased, there will be a lot of current injection here, lot of current will inject, and that current will essentially go and come here and will come out through the gate, or it will contribute to channel, which is what we do not want, okay. We don't want that. We do not want this substrate to inject current, electrons, and then holes, and which will go here and then it will affect the channel here. That we don't want, because then this will, what will happen is that your substrate will also be a channel, your substrate also will feed electron, it will be a channel, it will also be channel, this will also be channel, that will be defeating the purpose of the MOSFET. So what you actually, when you say substrate voltage on a p-type substrate, what you mean, and of course n type the polarity will be different. If I have a p-type substrate here and then channel is n, then obviously you mean that Vb or the body voltage has to be negative, so that this n plus p junction is actually reverse bias. You are depleting it more and more, you are not actually injecting carriers. So when I say substrate effect or body voltage or bias, I inherently mean that this is negative, maybe minus 1 volt, minus 2 volt or whatever, okay. So you are applying a negative voltage so that you are not injecting carriers here, but you are actually increasing the depletion, and your current here, your channel charge and your current that you are flowing in the channel between source and drain actually is going to get affected. So inherently I mean the Vb is negative, Vb is negative. So I can either say this is Vbs, because S is the source which is grounded, which is the same as Vb of course, this will be some negative quantity. In some textbooks they also say Vsb, and that is positive. What does it mean? Because Vsb is like the body voltage with respect to source. So Vsb essentially means that V source, this S means source, minus V body. If this is positive, essentially what it means is that this is 0 volt, and so this is negative, okay. That's what it means essentially, okay. This has to be negative. It's the same thing, the convention matters. Some textbooks say Vbs, and some textbooks say VSB. B is the body voltage and S is the source voltage. Source is always grounded here. So, when I say VBS, it means I am applying a negative voltage to the substrate. When I say VSB, still I am applying a negative voltage to the substrate. It always has to be negative voltage, but because it is VSB, this quantity will be positive, this quantity will be negative, but the VB is always negative. You see my point, right? VB is always negative here. It is how you write the convention. If you say VBS, it is negative. If you say VSB, it is positive, but VB is negative always. So, please keep that in mind. Okay. So, now question is, how will this extra substrate voltage that you are applying on the substrate will actually affect the threshold voltage? You will see that it actually can affect the threshold voltage, and that is why this extra body voltage or the substrate voltage that you apply is an extra knob or an extra tuning factor that can help you tune the threshold voltage independent of the other parameters. So, it is very nice in a way to actually control the threshold voltage. So, let us come to a figure here. You see, this is a figure I am taking from internet and many other resources that I will cite at appropriate times. You know, this is the source, this is the drain, and there is a channel that is forming. The substrate actually you can, this is VSB it says, so of course it is negative, VB is still negative. So, ESB is positive, the convention. Okay. So, you are applying some body bias here. What will happen is that if you do not apply any bias here, if you just kind of short it here to the source, to the ground, then this is how the band diagram will look like along the channel. But the moment you have an extra bias, you will be bending the bands even more, because at this point, this junction between the N plus source, and P substrate, this junction will become reverse biased, okay. And because it becomes reverse biased, you will have this band bending that is occurring here, right, this extra band bending that is occurring here, and that band bending is occurring because of this term VSB, okay. This VSB term is actually occurring an extra band bending here, and so what you can do is that for example, when you try to solve the gradual channel approximation and all the equations that you derive, the surface potential along this, you know, I told you that the moment you have inversion, you have in this direction you have a band bending of 2 phi f at strong inversion, but along this direction, because you are also applying a VDA here positive with respect to the source ground, along this direction, because you will be applying that, you have to apply that term, you know, V of x at any point x here. Of course, at this point it will be VDS, but at any point will be x. So, this is the voltage actually that at any point x you will see here in the absence of any body bias, when the body is shorted to the source. But in the case the body bias is also, you know, there is some finite body bias you are applying, you have to, it is VBS should be subscript here, sorry. So, you have to subtract out that body bias, essentially VBS is negative quantity, so that negative and negative essentially becomes positive, okay. So, this quantity will be like minus 1 volt or minus 2 volt. So, this minus 1 volt will make it positive, okay. So, that is what I am trying to say. So, what I am trying to say here is that this is typically the voltage that you are dropping at any point x because of the drain voltage that you are applying and the inversion that is happening here, okay. The inversion that is happening, and there is a potential in this direction, and band bending in this direction, sorry. But because of the substrate voltage, you have to have an extra drop here, because that will increase this to here. So, now you solve the, okay, because of some formatting issue it has come like that. This is again VFB essentially, this is superscript here, Cox superscript here, anyways. So, you know, this is the total charge that will be there in the channel at any point x. We have derived this expression previously, but here there will be one extra term here, and that is you see, this is the expression that we had derived previously in the absence of body bias. In the presence of body bias, this quantity will be replaced by this quantity, and this quantity also will be replaced by that quantity. So, it will become like this, sorry, okay. You see this, it has become like this, okay. So, you have Vx minus Vbs, and then again Vx minus Vbs that you have. So, now if you know this charge, because it is in the presence of a body effect here, you can actually derive the current voltage characteristics, you can derive the threshold voltage also, and it so happens that in the presence of this kind of a term here, now the threshold voltage will shift by some amount. This is the current in the linear regime, this is the current in the saturation regime, everything stays same except the threshold voltage has changed, it has become V dash Vth. So, this threshold voltage has changed, but everything else remains same, and this threshold voltage change is, this is the new threshold voltage by the way, okay, because of the substrate effect. You see the substrate effect has come here, can you see that this substrate effect has come here. If you do not have that substrate, then it will reduce to the original expression that we had, and so this is that extra, this is the extra threshold voltage change that happens because of the substrate effect. this is 2 epsilon q square under square root with Na. This is the doping, of course Na is the doping of the substrate, the p type substrate. Cox is the capacitance value, and this is 2,5 is the band bending. VBS actually this B should be like this. So VBS is the extra voltage they are applying. This is the negative quantity, typical, it has to be negative quantity. So what I am trying to say is that this negative sign and the negative quantity will make it positive. Okay, so that keep it in mind. And if your VBS was 0, which means you are actually grounding it and there is no difference, then this quantity will become 0, and so this quantity will become 0, and so the delta VH, you know, the threshold voltage shift will not happen. So what basically it means is that by changing the bias on the substrate, I am able to change the threshold voltage. So the threshold voltage will change roughly as the square root of this, you know, subtracted from this square root. So if you apply more and more substrate bias, you are able to actually change the threshold voltage as a square root sort of a dependence. Okay, so this is an extra knob that designers use to actually tune the subthreshold voltage, to actually not subthreshold, to actually tune the threshold voltage. Okay, so that's, you should keep that in mind. So we have finished this two part now. Okay, we have finished the gradual channel approximation. Also we have finished the substrate bias effect. So the next thing will be subthreshold slope now. Subthreshold conduction and subthreshold slope are very, very important in modern day electronics, especially for very low power devices, low power, you know, low power chips, where you want very, very low power, ultra low power, extremely low power, but you need a very high on off ratio, which means the current, you know, if I plot ID versus Vg gate voltage, I should be able to go from off state to on state very sharply, okay, very sharply at very small voltage. So if this voltage range is very small, that means it is a low power device. You do not have to go much higher like this, you know, to go from very low current to very high current, you do not have to drop much large voltage. So this, you know, sharp threshold sort of a, this actually is a very important concept, and that is why research on this area is very hot even today. New materials are discovered. What is subthreshold conduction? Subthreshold conduction is the conduction below threshold, right? It is just conduction below threshold. You know, before you go to strong inversion at threshold voltage, before you go to strong inversion at threshold voltage, you have weak inversion. In weak inversion, your bands are bending sufficient such that now your formula, your intrinsic level is touching the Fermi level. You know, this weak inversion is taking place now, and it's also going below the Fermi level. The Fermi level is going below the intrinsic level. The intrinsic level is going below the Fermi level. So you have some weak inversion. You have not reached strong inversion, but still it will carry some current, very low current, but it will carry some current. That is called subthreshold conduction. So actually, if you plot ID versus Vg on a linear scale, I keep telling you that, you know, threshold voltage, if the threshold voltage for example is say Vg is equal to say 1 volt. So this is 1 volt, this is 2, this is 3 and so on. Then below 1 volt the current will be almost negligible here, and at 1 volt threshold the current will increase. That is what the threshold voltage means in an, this is called transfer characteristics, by the way. I have drawn it even earlier. Transfer characteristics essentially show the output current ID versus input voltage Vg. This part is actually the subthreshold conduction. You will see that this current is almost 0. This is current, for example, maybe this is 1 milliamp, this is 5 milliamp, 2 milliamp, 5 milliamp and so on. So this point, you know, below threshold we see that there is almost no current, and so we call it subthreshold conduction. Now you might say that the current is very, you know, almost 0 here. So you know, how what do you talk about subthreshold conduction? Actually the current is not 0, the current is very low but it is not 0, and the current will actually come up only in a log scale. Only if you plot this in a log scale you will see the current actually come up. Okay. So what do I mean by that is that the same plot if I do in a log scale, this is log of ID versus, this is log of ID versus Vg at 1 volt, 2 volt, 3 volt for example. You see below 1 volt, okay, let me change the color here probably. Below 1 volt, it was in a linear scale, this was linear scale, and so you see that this current is almost 0 here and then it rises at threshold. But here you will say that this is actually log scale. So this could be say 1 picoamp, 1 nanoamp, 1 microamp, 1 milliamp. So this is 3 orders of magnitude. 1 pico to 1 nano is 10 to the power 3 difference. I mean times difference, 1 pico, 1 nano to 1 micro, 1 micro to 1 milli, you know, this is like 1 order of magnitude difference. So what will happen is that it's 3 orders, 6 orders difference here, right. So what's going on here is that below 1 volt, actually from 0 to 1 volt, your current will actually increase like very sharp, you see on the log scale. This will not show up here because it's here milliamp only, linear scale will not show up. So up to 1 volt, and then from 1 volt the slope will change. There is a slope here very sharp, and then the slope changes here. This part is what you see here, this part from 1 volt, because it is a linear scale. In this linear scale you can see from 1 milliamp, 0 milliamp sort of to few milliamps current you will see here, right. But below that, when you have microamp, nanoamp, picoamp of current, that will not show up in a linear scale, it will show up in a log scale. This is the subthreshold, I call it SS, subthreshold conduction. There is a conduction, and this it is rising by many orders of magnitude. It is rising from pico to like micro, hundreds of micro. It is rising by many orders of magnitude in a very less voltage. You do not see it in a linear scale, you only see it in a log scale. This slope is actually called subthreshold slope. Subthreshold conduction and subthreshold slope. This slope is subthreshold. The steeper this slope is, you know, higher, the lower is the subthreshold slope, and better the device is. If you have steeper device here, a steeper slope here, if the slope becomes steep, much more steeper, it means your device is turning on and off very sharply, and that means at very small, by expending very small gate voltage, you are able to turn on the channel by many orders of magnitude. That is called steep slope. So sharp, very sharp on and off. That means you are able to operate the device at much lower power, low voltage, and this is subthreshold conduction, this is subthreshold slope. If your slope is bad, which means suppose, you know, you have to go from here to there in a very slow, this is a very bad slope, right. This is a not so steep slope, this is a less steep slope, right. So it will go like this. That means to go from this picoamps to sort of milliamps, you have to drop like 3 volts. Over here you are dropping only 1 volt. So you see here you have to drop 3 volts. That means the power that you supply to your Mosfet, and these are like Mosfets, these are millions and billions in numbers in your processors, in your mobile processors, or in your laptops and all. So you know, you have to turn off and on the Mosfet. You know, digital logic works like 0 and 1, for example, memory devices work, many things are there. So anytime you have a logic device, and you know, this all your processors, by the way, all your cell phones, laptops are working on that only. So to have this logic devices work in your processors, you have to spend 3 volts of power on each Mosfet, actually, or voltage on each Mosfet. So the supply voltage that you are putting on the chip has to be at least 3 voltage, and then only it will come to milliamps from picoamps, for example, and that milliamps to picoamps is necessary for defining the on off ratio, or for defining the 0 and the 1 state of the digital logic, right. So you have to spend 3 volt, that is a lot of voltage, that is a lot of power, you are wasting power. It will be better to have a transistor which can do it in, for example, 0 to 1 volt. In that case, it is such a steep slope transistor that you can supply only 1 volt to your chip, your 1 volt to your mobile chip. So your source volt, when I say source, you are supplying the voltage, the supply voltage to your mobile phones or whatever in the chips will be only 1 volt. You are able to turn on the device by so many orders of magnitude, it's just sharply. So these are called steep. You know, you want the slope to be steep, and the steeper the slope is, the more low power the device is. Instead of 0 to 1 volt, if you actually can go from 0 to 0.5 volt and you can raise this, then that's a even fantastic number. Okay, so you want, people are trying to go to low and low power logic, and for that you want to do, you know, of course, low power. So your cell phone battery will last longer. If you have to you can go by this order of magnitude change in current, that is the on off ratio, the digital 0 and 1. If you can change so many orders of magnitude of current in very low voltage, say 0 to 0.5 voltage, that means your battery has to supply lower power, which means your cell phone battery, your smartphone battery will last longer. Your cell phone battery will last longer, you have to charge it less, right. It will be very convenient. If on the other hand, if your voltage, you are applying 3 volt to turn on and off each Mosfet in your cell phone, there are millions, billions of Mosfets, then you can imagine that your cell phone battery will dry out soon, because you have to apply so much voltage. So that is the practical correlation I was talking about in this course, that you know, whenever we try to understand these devices, we have to also see in the light of practical devices what is going on here. So this subthreshold slope, I call it SS, and subthreshold conduction are very important concepts that are important in modern day electronics, modern day devices, and that is why the next thing that we will study now will be subthreshold conduction. We will just go through what is subthreshold what is the equation for subthreshold slope, and from there we will see that there is a fundamental limit which MOSFETs can actually possibly work. Okay, and after that we will finish up the short channel effects in the devices. Okay, so with that we will end the class today, and we will come back in the next class with we will continue with subthreshold conduction and short channel effects. So that will basically wrap up our lectures for MOSFET. We will be done with that. From there we will take up other topics, but I hope that you have understood the basics of MOSFET. We have not gone into very deep advanced mathematics into many of these things, but whatever basic mathematics is required we have used those so that you are familiar with the equations for current, voltage relation, transconductance and other things. Okay, so let's meet in the next class and we'll take up from subthreshold conduction. Thank you.